Hello, everyone, and welcome back to the Graduate Online Combinatorics Colloquium. Today, we have Aaliyah Dawkins speaking, but before I introduce her, I wanted to remind everyone of our community statement. So the GOCC has three core principles. You can find the full statement on our website, but the principles are: one, we are all learning; two, everyone has something to contribute; and three, no one has all the answers. And so if you have questions during the talk, feel free to unmute yourself and present them to Aaliyah, or you can type them in the chat, and one of the organizing committee will make sure that it is transferred to Aaliyah. But may I introduce Aaliyah Dawkins from George Mason University, speaking about the edge condition for Hamiltonicity and KR+1 free graphs. Aaliyah, take it away.
Yeah, thank you, Mark, for the introduction. Yeah, so this is joint work that I did along with my advisor, Rachel Kirsch. And let's see, can I change slides? Yeah. First, I'll start off with just introducing the definitions and the motivation behind the research, some preliminaries that we'll need to understand the proof and the results, and then some directions that I hope to take the research. So, as much as I would not like to admit it, combinatorics is not all graph theory. So I'm going to make sure to go through what graph theory really is and just some basic definitions to understand all of the results. So in extremal graph theory, we're often studying how large a parameter of a graph can be if the graph satisfies certain properties. And this is great because it allows us to tell how many edges or vertices are in a graph if we know nothing about the graph other than like one property about it. And the first property that we're going to be concerned about is going to be being F-free. And we say that a graph is F-free if it does not contain a subgraph that is isomorphic to F. Right, so for example, this graph here is triangle-free, meaning that no three vertices are going to create a triangle. And this graph is also what's known as a bipartite graph, bi meaning two, and partite telling us that we're dividing our graph or our vertices up into parts. So the parameter we're going to be concerned with is the number of edges. And with that parameter and this property, that's known as the Taran problem, which determines the maximum number of edges in a graph that is F-free. And Taran studied this problem himself for r-cliques. And an r-clique, which we'll just denote as KR, is just a set of R vertices, all of which are adjacent, right? So for example, here is a 4-clique. 4 vertices, all of which are adjacent. So what Taran was able to show is that if your graph is KR+1 free, then the number of edges in your graph, which I'll denote as little e of g, is at most the number of edges in the Taran graph. And the Taran graph is the n-vertex complete r-partite graph with its parts as balanced as possible. So, for example, when n is 11 and r is 4, this would be the Taran graph. So it's going to be the 11 vertex graph that is 4 partite. So our 11 vertices are going to be divided up into the 4 parts with our parts as balanced as possible, meaning that the sizes of any 2 parts can differ by at most 1. And then it's complete, meaning that every vertex is connected to every other vertex outside of its part. And Taran was also able to show that equality holds if and only if G is the Taran graph. So Ore studied a similar question, except he replaced the property of being F-free with the property of Hamiltonicity. And a graph is Hamiltonian if it contains a Hamiltonian cycle. And that's just a cycle in your graph that visits every vertex exactly once. So what Ore was able to show is that if your graph is not Hamiltonian, then the maximum number of edges in your graph is n-1 choose 2 plus 1. And we're going to get equality if and only if G is the complete graph on n-1 vertices plus a pendant edge adjoining that last vertex. So for example, when n is 11, we would have this graph here, right? A complete graph on 10 vertices, and then that last vertex adjoined with a pendant edge. So what Rachel and I decided to study is the intersection of these two problems. So we wanted to know what is the maximum number of edges in a graph that is both kr+1 free and not Hamiltonian? Right. And spoiler alert, we did answer this question, but before we get into the answer, we're going to go ahead and talk about some of the results that came before this and the idea of what really motivated our extremal graph. So the first result I'd like to talk about is this theorem by Adamus, who addressed this problem for tripartite graphs. And Adamus was able to show that if you have a balanced tripartite graph that is not Hamiltonian, the number of edges in your graph is at most the number of edges in the Turon graph on n-1 vertices plus 1. And Ferrero and Lesniak in 2018 were able to extend this to r-partite graphs in general. And they were able to show that if your graph is r-partite and not Hamiltonian, then the number of edges in your graph is at most the number of edges in the Turon graph on n-1 vertices plus 1. And here's an example of a graph that would obtain that maximum number of edges. As you can probably guess from the edge bound, it's going to be the Turon graph on n-1 vertices, and then that 1 is going to come from that pendant edge to join that last vertex. Great, so we used this idea from Ferrero and Lesniak to also address the kr+1 free case, because if your graph is kr+1, it happens to be r-partite. So we're looking at the larger class on top of this, right? So what we were able to prove is that if your graph is kr+1 free and not Hamiltonian, then the maximum number of edges in your graph is the maximum number of edges in the Turon graph on n-1 vertices plus 1. And we're going to get a quality if and only if G is the Turon graph on n-1 vertices plus a pendant edge. Right, so we were able to encompass that corollary from Ferrero and Lesniak. And just as their extremal graph goes, ours goes. So our extremal graph is going to be that Turon graph on n-1 vertices plus the pendant edge. And here's that example when n is 11 and r is 4. And what I really love about this result is not only are we looking at the intersection of Turon and Ore's problems, but we are also intersecting their ideas for the extremal graphs. So we're really taking Turon's idea to make sure it's kr+1 free to maximizing the number of edges, and then Ore's idea of adding that pendant edge, right, to make sure that it's not Hamiltonian. Okay. So now that we understand what the main result that we're trying to prove is, let's go ahead and talk about the methods that we used to prove them and the proof. So the methods that we used are degree conditions. And in particular, for non-Hamiltonicity, I used this degree condition from Chavital. Chavital showed that if G is not Hamiltonian, then for some J between 1 and n-1 minus L over 2, we're going to have that jth vertex degree is at most J plus L, and the n minus J minus L vertex degree is at most n minus J minus 1, where L equals 0. And I know it's weird that I didn't just plug the 0 in and I put this general form with the L, but we'll see later on why I did that. And it's because I proved the theorem in a very general way, because there are other Hamiltonian-like conditions for different L values. But again, we'll discuss those later. Okay, so this is the degree condition that we want to apply to our theorem to get our main result. So before we get into the proof, let's talk about the extremal graph families that our extremal graphs can live in. So for lower values of n, we actually have another extremal graph option, which we'll talk about. So the two families that we have are what I'll call the G family, and the G family is the family of n vertex kr+1 free graphs consisting of the Turon graph on n-1 vertices plus a vertex of degree L plus 1. And the second family, which I'll call the H family, is going to be the family of n-vertex KR+1 free graphs consisting of the Turon graph on n+1 plus L over 2 vertices, plus an independent set of n-1 minus L over 2 vertices of degree n-1 plus L over 2. And with these vertices, since we're going to first look at the case of non-Hamiltonicity, we'll want to know when these extremal graphs are not Hamiltonian. And it turns out if your graph is in the G family and L equals 0, well, then your graph is not Hamiltonian, right? So pretty straightforward with that one. And then for the H family, if L equals 0 and G is not Hamiltonian, well, then that tells you that G has to be the complete multi-partite graph with one partite set of size n+1 over 2 and the other partite sets of size at most 2. And both of these propositions are going to help us classify our extremal graphs, as we'll see in the main result. Okay, so the theorem that I actually proved and used to apply the degree conditions to was this one here. And what I was able to show is that if G is an n-vertex KR+1 free graph with vertex degrees d1 through dn, and if there was a j between 1 and n-1 minus L over 2, such that that jth vertex degree is at most j plus L, well, then the number of edges in G is at most the edges in the Turon graph on n-1 vertices plus L plus 1. And furthermore, if we have equality, then either j is 1 and G lives in that G family, or j is n-1 minus L over 2 and G lives in that H family.
Can I ask a question?
Mm-hmm.
So on the previous slide, so your Turon graph can be, so it has balance, but like some of the parts can have more vertices than the other parts.
At most, yeah.
Yeah, at most one. So when you are introducing this new vertex of degree L+1, is there a condition on which part it can send an edge to?
Generally, we put it into the smallest part just to make sure that we keep it balanced, but ultimately it doesn't matter, I guess.
Interesting. Okay. Okay.
Yeah. Any other questions? Great. Okay. So yeah, now we'll go on to proving this theorem. So, right, suppose that there is a j between 1 and n-1 minus L over 2, such that that jth vertex degree is at most j plus L. But then what we're going to do is we're going to let big J be the subgraph in G that's induced by those j vertices, and we'll let H be the remaining part of G. So what we've done is we've taken our graph G and we've pulled out those j vertices, which we're representing as J. We've let the rest of the graph be H. And of course, there may be some edges between J and H, and we'll let that be denoted by the boundary of J. And so what we have is that the number of edges in G is precisely the number of edges in J, plus the size of the boundary of J, plus the number of edges in H. And then we can bound the number of edges in J and the number of edges in the boundary of J by J squared plus LJ. And that'll just come from the degree conditions on those J vertices and the fact that their degree is at most J plus L. And then we'll bound the number of edges in H just using the Turon's theorem because we know it's a subgraph of G, which is KR+1 free. And then after a bunch of painful algebra, we'll end up getting that the number of edges in G is at most the number of edges in the Turon graph on n-1 vertices plus L plus 1. Okay, so this was the proof sketch and pretty much how it went for R at least 4. For R equals 3, it was a bit more difficult. I'm not going to go into that proof at all, but if you have questions about it, I could answer it at another time. But for R equals 3, basically what I had to do was additionally pull out disjoint copies of K3 along with this method. Okay, so that was the main. Yeah.
How does R greater than equal to 3 play a role here?
How is it different?
Yeah, why is R greater than equal to 3 important in this proof sketch?
So this I was just saying for r equal to 3, this method doesn't work. This is only for r at least 4. Yeah, and for r
Yeah,
equals,
why?
it's in the algebra. So
Okay.
yeah, it's all in the algebra.
Okay.
Because when r equals 3, at some point I'm dividing by r minus 3, and I can't divide by 0. So it doesn't work out.
Okay. Cool. Great.
Yeah. Okay. Yeah, so next I will talk about the lemma that's going to allow us to say precisely when our extremal graph lives in either the G family or the H family. Right, so this lemma is telling us that for that case where J equals n minus 1 minus L over 2, and we have equality, right? So in the case that G lives in that H family, that can only happen when one of these 4 conditions is true, right? If r equals 4 and n is between 5L plus 11 and 13 minus L, or the other 3 that are listed there. So with the theorem and with the lemma, I'm able to plug in the value L equals 0, which corresponds to being not Hamiltonian, and I'm able to get this result here. So what I precisely showed was that if G is kr+1 free and not Hamiltonian, then the number of edges in G is at most the number of edges in the Tron graph on n minus 1 vertices plus 1. And then equality is going to hold if and only if G is either in that G family, or G is K6,222, K4,111, or K5,1111. With those 3 exceptional cases happening when R is 4 and N is 11, R is 5 and N is 7, or R is 5 and N is 9. Okay. So as I said before, right, I proved this very generally with that L value because for different L values, it's going to correspond to different Hamiltonian-like properties. So when L is -1, it's going to correspond to traceability. And when L is 1, it's going to correspond to Hamiltonian connectedness, for instance. And those are the 2 I'm going to focus on right now.
Can we quickly go back a slide? Because I was trying to do some visualization in my head and I realized my visual was wrong. 4 and 1.
Or the next one?
The next one.
Okay.
So right. Is K5,1111 not Hamiltonian?
It's not. And the reason is because for a graph, for a complete graph to be Hamiltonian, the largest part can be at most half the number of vertices. So 5 is strictly more than 4, so it's not Hamiltonian.
Okay. Okay, thank you.
Any other questions? Okay. Yeah. So the next 2 properties I'd like to talk about are traceability and Hamiltonian connectedness for the L values of -1 and 1 respectively. And a graph is traceable if it contains a Hamiltonian path, just being a path in your graph that contains every vertex of your graph. And a graph is Hamiltonian connected if every pair of the vertices is connected by a Hamiltonian path. And just as with Ori's result for being non-Hamiltonian, Ori also had results for being not traceable and not Hamiltonian connected. So if G is not traceable, then the number of edges in G is going to be at most the number of edges in the complete graph on n-1 vertices. And we're going to have equality if and only if G is the complete graph on n-1 vertices plus an isolated vertex. And if G is not Hamiltonian connected, then the number of edges in G is going to be at most the number of edges in the complete graph on n-1 vertices plus 2. And we're going to have equality holding if and only, or no, equality holding if G is the complete graph on n-1 vertices plus a vertex of degree 2. Okay, so here are the examples of those extremal graphs for n equals 11. So for the non-traceable case, we're going to have the complete graph on 10 vertices plus that isolated vertex. And then for Hamiltonian connectedness, we're going to have the complete graph plus that vertex of degree 2. And so you can see the similarities to the non-Hamiltonian extremal graph, which have that pendant edge instead. And you can also probably take a guess on how we're going to combine this with Turan's theme and create the KR+1 free, non-traceable extremal graph and the non-Hamiltonian connected graph.
So I think I've discovered that I am something is wrong in my head.
Mhm.
Hamiltonian connected. So between any two vertices, there's a Hamilton path.
Mhm.
Hamilton path is a path that visits all the vertices.
Yes.
On my not Hamiltonian connected graph on the right, how can I not just always go around the boundary of this polygon that you've created? So pick, oh, right, because they're not adjacent.
Oh, we have that isolated vertex. Yeah, so traceability
Yeah,
is
no, the one on the left, I believe.
But yeah, that's a good point. So traceability is actually a weaker condition than Hamiltonicity. And you can kind of see it from the extremal graph, right? Because we have that a bit less of a connection. And then Hamiltonian connectedness is a stronger condition. So this extremal graph actually is Hamiltonian, right? By going around the outer cycle, but it's not Hamiltonian connected.
Which pair of vertices fails?
So it is the pair of vertices that are adjacent to that special vertex.
Okay.
Because
Makes sense.
if you want to go around to connect everything else, you can, but then you're missing out on that special vertex of degree 2.
Thank you.
Mhm. All right, yeah, great question. All right. So just like with Hamiltonicity, we also have degree conditions for traceability and Hamiltonian connectedness due to Chavatal and Burge. So Chavatal showed that if G is not traceable, then for some J between 1 and n minus 1 minus L over 2, we have that jth vertex degree is at most J plus L, and that n minus J minus L vertex degree is at most n minus J minus 1, where L is -1. And Burge showed that if G is, a little typo, is not Hamiltonian connected, then for some J between 1 and n minus 1 minus L over 2, we have that jth vertex degree is at most J plus 1, or J plus L, and the n minus J minus L vertex degree is at most n minus J minus 1, where L is 1. Right, so all of these degree conditions have the exact same layout. The only difference is what their L values are, which is why I was able to generalize the results to that general theorem so well. Okay, and just as with the Hamiltonian case, when L equals 0, we're going to have that if G is in that G family where L is -1, G is not traceable, and if L is 1, G is not Hamiltonian connected. And if G is in that H family and L is -1, and G is not traceable, well, then G is going to be the complete multi-partite graph with one of its parts of size n plus 1 over 2, and the other partite sets of size at most 2. And if L is 1 and G is not Hamiltonian connected, then G is a complete multi-partite graph with one part of size n over 2 and the other partite sets of size at most 2. Okay. So with all of that, we were able to plug in our L values into the main theorem and get these nice results here. So if G is KR+1 free and not traceable, then the number of edges in G is at most the number of edges in the Turan graph on n minus 1 vertices, with equality happening if and only if G is the Turan graph on n minus 1 vertices plus that isolated vertex. Or we're going to have G being K411 or K521, with those exceptional cases happening when R is 4 and N is 6, or R is 4 and N is 8, respectively. And if G is not Hamiltonian connected, then the number of edges in G is going to be at most the number of edges in the Turon graph on n-1 vertices plus 2. And we're going to have equality holding if and only if G is in that G family. Okay, so looking at those extremal graphs, you can really see how, again, we're using Turon's idea for the KR+1 free and Ore's idea for the Hamiltonian conditions and combining them to get our extremal graphs. So for KR+1 free and non-traceable, we have the Turon graph on one less vertex plus that isolated vertex. And for non-Hamiltonian connected, we're going to have the Turon graph on one less vertex and then connect it to two of them. Right, so those were the results for R at least 3. And we did also adjust it for R equals 2, right? So when G is a K3 free graph. And for these, it's a bit different, and it actually fits more along the lines of Turon's and like Mantel's extremal graphs, because we're still having them be complete graphs, complete bipartite graphs. So if G is K3 free and not traceable, we showed that the number of edges in G is going to be at most the number of edges in the complete graph with parts of size, the floor of n over 2 minus 1 and the ceiling of n over 2 plus 1. If G is not Hamiltonian, then the number of edges in G is going to be at most the number of edges in the complete graph with parts of size, floor of n over 2 and ceiling of n over 2 for n odd, and n over 2 minus 1 and over 2 plus 1 for n even. And if G is not Hamiltonian connected, then the number of edges in G is going to be at most the number of edges in the complete graph with parts of size, the floor of n over 2 and the ceiling of n over 2. Okay, so those were the results for Hamiltonicity, traceability, and Hamiltonian connectedness. And then there are 2 more extensions that I'd like to talk about. The first one being to chorded pancyclicity. And if you're unfamiliar with what it means to be chorded pancyclic, pancyclic just means that your graph is going to contain a cycle of every size between 3 and the number of vertices it has. And chorded means that every cycle of size at most 4 is going to have a chord, which just means an extra edge in the middle that's not on the boundary of the cycle. So what Chen, Goud, Gu, and Sato were able to show in 2018 is that if we have a Hamiltonian graph that has at least n squared over 4 edges, then that graph is chorded pancyclic, or n is even and G is the bipartite graphs with even part sizes, or G is the Cartesian product of K3 and K2, which if you're unfamiliar with Cartesian products, it's just like the one skeleton of the triangular prism. Okay. So what Rachel and I were able to do was use our theorem for KR+1 free and non-Hamiltonicity, along with this theorem from Chen, Goud, Gu, and Sato to get the following corollary. So we were able to show that if G is an in-vertex KR+1 free graph that's not chorded pancyclic, then the number of edges in G is at most the number of edges in the Turon graph on n-1 vertices plus 1. Right? And just thinking about why this is true, it's easier to see in the contrapositive, right? So suppose that we had strictly more than this number of edges, right? Suppose we had strictly more than the Turon number of edges on n-1 vertices plus 1. Well, then by that theorem the main theorem that we talked about before, that would imply that our KR+1 free graph would have to be Hamiltonian. So by this theorem from Chen, Goud, Gu, and Sato, and the number of edges that we know that our graph has, that would imply that our graph is chorded pancyclic. So we would get this corollary exactly, with those extra cases ruled out by the number of edges and the number of vertices. Okay, so that was the chorded pancyclicity extension. And the next extension I'd like to talk about is to clique conditions. Right, so the theorem that we the main theorem that we proved was for the number of edges that would imply your KR+1 free graph is Hamiltonian or not, but then we were able to extend these to clique conditions for the same properties. So before we get into those conditions, I'd like to just talk about the Collex order a bit and the Collex-Turan graph. So the R-partite Collex order is the restriction of the Collex order to the pairs of integers ij, where I is not congruent to j mod r. Right, so you're just looking at the Collex order of a bunch of pairs of numbers, and you're just removing the ones where I is congruent to j mod r, and you're not using those. And if you're unfamiliar with the Collex order, it's just based off the symmetric difference. It's just a way to order pairs. So the R-partite Collex-Turan graph on M edges, which we'll denote as CT sub R of M, has the edge set consisting of the first M pairs of those natural numbers, where I is not congruent to j mod r in the R-partite Collex order. And its vertex set is going to be the union of all the edges, right? So the subset of n that's needed to support the edges and avoid isolated vertices. So what Frometer showed was that if your graph is KR+1 free with at most M edges and T is at least 2, then the number of T cliques in your graph, which I'm going to denote as K to the T of G, is at most the number of T cliques in that R-partite Collex-Turan graph on M edges. So what Rachel and I did was take this theorem and extend it. We wanted to look at KR+1 free graphs that satisfied a property on top of this. And we wanted to show that they also maximize the number of T cliques. Right? And that's exactly what we did. Right? So we showed that if you have a KR+1 free graph, which does not have some property, we'll call it A, and if the R-partite Collex-Turan graph does have that property, well, then it's still going to maximize the number of T cliques over all those graphs. And this upper bound is tight, as equality holds when G is that R-partite Collex-Turan graph. Right, and just as we want, the R-partite Collex-Turan graph lives in this G family, meaning that it's going to be that graph that's maximizing the number of T cliques, that is KR+1 free and not Hamiltonian when L equals 0, not traceable, not Hamiltonian connectedness, depending on your L value. Right, so what we're able to do is use those theorems along with our main results to get these clique conditions here. So if we let G be a KR+1 free graph and G is not traceable, then the number of T cliques in G is at most the number of T cliques in the Turan graph on n-1 vertices, with equality being when G is the Turan graph on n-1 vertices plus an isolated vertex. If G is not Hamiltonian, then the number of T cliques in G is going to be at most the number of T cliques in the Turan graph on n-1 vertices plus a vertex of degree 1. And if G is not Hamiltonian connected, the number of T cliques in G is at most the number of T cliques in the Turan graph on n-1 vertices plus a vertex of degree 2 whose neighbors are adjacent. And this distinction of the neighbors being adjacent really is the biggest difference between the clique conditions and the edge condition. Because to maximize the number of cliques, we're going to want to make sure our neighbors are spread out between the parts as much as possible. Okay, so those are the major results that we got during this research. And as for moving forward, there's a couple ways that I'm hoping to take this. The first being I would like to look at the maximum number of edges in the n-vertex KR+1 free graphs that are not Hamiltonian, which are also not R-partite. So if you remember, the extremal graph that we had was based off the Turan graph, so it was R-partite. So if we put this extra condition on it, what would that do to the extremal graphs and the maximum number of edges? And additionally, what is the maximum number of edges in an n-vertex KR+1 free non-Hamiltonian graph, which is two connected? Right, so our extremal graph is getting non-Hamiltonicity kind of in a very lazy way, which is having that pendant edge to guarantee that it's not Hamiltonian. So what meaning that we can make one cut and disconnect our graph. So what if we require it to be two connected, meaning that we need at least two cuts to disconnect our graph, right? How would that affect our extremograph and our edge bound? Right. And thank you all for listening. Are there any questions?
Okay, yes, thank you, Aaliyah. While questions form themselves, if you could go back a slide.
Yes.
So in your current directions, you gave what the extremal graph, the Turan graph for the KR+1 free graph is, but ignoring the non-Hamiltonian condition, what do KR+1 free non-R-partite graphs, like what is the extremal case just for the, when you forget the Hamiltonian condition there?
Off the top of my head, I don't remember what they are. I do know that they're known though.
Okay.
So when I do approach this question, or whoever approaches this question, that's where they should start. Yes.
I did have more questions, or mostly just more examples of extremal cases of graphs, because I like looking at pictures. Like way back near the beginning of the slides, I can't remember which slide this was on. There was something that was like, oh, well, all the graphs look like this, except for the exceptional case of n equals 5.
Mm.
And I was just like, well, what's the n equals 5 case? Like, that's small enough you can draw it, right?
Which one was it? The Turan one?
Probably, almost certainly, but because it was like in like, yes, the or theorem, like you've got one exceptional graph and you don't even show us a picture of the exceptional graph, but it's exceptional.
That's why I didn't want to do it, because it's the only case it happens.
Exceptional like exception, not exceptional like it's a wonderful graph. Really?
No. So for n equals 5, that's the only like vertex number where you have two possible extremal graphs. So that's why I didn't want to pick it, because I didn't want you guys to be like, oh, like maybe that's what it looks like. It's like, no, it never looks like that.
Wait, what does that one look like?
Yeah.
Now I want to know.
Let me think about it for a second. I believe it's some type of complete multipartite graph.
So, I mean, 5 vertices. Okay. It's like I can draw 5 vertices. Yes.
I think it might be the 3 triangles inside each other.
The 3 triangles inside of each other. That is not a graph I have in my head.
Sure. I might be wrong, but is that the same? Is that different?
So that's K32?
Mm-hmm.
No, it's not.
No,
It's not.
not quite. K311. That's what it would be.
Yes. I am unable to find a Hamilton path in this, or a Hamilton cycle. I can find a Hamilton. Well, can I find a Hamilton path? No.
No, yeah, it's not possible.
Yeah.
Yeah, I was like, oh
Oh.
no, I can't find a Hamilton path. I looked again, I'm like, no, I can't.
Yeah, anytime the largest part is bigger than the rest of the part, it's
Mhm.
not Hamiltonian.
Also,
For
like
example-
at the vertex, is it like the degree 3?
What was that?
So at the vertex, there's a degree 3 vertex, right? Like on the
Mhm.
bottom. Yeah. Okay. Okay. So yeah, that will be an issue when you're trying to come back. Okay.
Are there any other questions? Mark?
Not off the top of my head, no. So I think we can all thank the speaker again.
Thank you all. Yeah, thank you all for coming, for listening.